Number 87 shows a cross-section of a long conducting coaxial cable and gives us radii A, B, and C. Equal but opposite currents I are uniformly distributed in the two conductors. Derive expressions for the magnetic field for a radial distance r in the range of r less than C, r between C and B, r between B and A, and finally r greater than A. Test these expressions for all the special cases that occur to you. All right. So, first of all, we're going to be using Ampere's law, and for the first one, we're inside of that conductor. To do this, then, we have to figure out what fraction of the current is inside of this little red area here of radius r compared to the current through this whole region here. And so we can do that by just taking the area of the red shaded region over the area of that entire conductor, which has a radius of c, times the current, which I'm going to just write as I. The length of my Gaussian surface is going to be 2 pi r, where r is the radius. I realize here I've got r drawn all the way out there, but don't worry. If you simplify that down, you'll discover the magnetic field simply given by this. So it increases linearly all the way out to from 0 to c. What about in between? Well, here, that Gaussian surface is going to include all of the current in that inner conductor, which is I. So solving it, this one's actually easier. Gaussian surface still has a radius of r. Current now is I, and so that simplifies down to this expression. So for r between C and B, it's given by this. What about when it's over here, and that radius that's drawn there? Well, here you got to be a little bit more careful. It encloses all of the current here from the inner conductor, but it only includes portion of the current going in the opposite direction in this region here. So we've got to actually figure out what the net current is inside of my Amperian loop. To do that, we've got to do a little bit of algebra. Don't panic. So all the current I plus a fraction of the current, which is going to be equal to the shaded area of this divided by the total area of this outside conductor, which is going to be pi a squared minus pi b squared. That's a really hideous expression, I admit it, but you can simplify it down as far as you can. I don't think you can go much further down to this. Not pretty, but you've got r squared up here and r down here, and this is valid for this region. Finally, what if you go on the outside? Well, if you go on the outside, you're going to include all of the current going one direction plus all of the equal current going in the opposite direction. What's going to happen in this case? Well, the total current now is going to be 0 because you have both of these going on. So just I minus I. What's the magnetic field? It's going to be 0 once you get on the outside of this thing. And now ES, test these expressions for all the special cases. Well, take a look at this real quick. What happens when R reaches C? Well, when R reaches C, if you think about it, if R becomes C, what happens? This expression, and think of R is equal to C, you get C divided by C squared or just over C. Well, that's exactly equal to this expression when you plug in C. What does that mean? Well, it means that this expression is all the way valid out to C. And this equation down here is also valid. And you might say, whoa, wait a second. Yeah, all the way out to B. If you plug B in for R down here, you end up with C squared minus B squared over C squared minus B squared. That's 1. And so this expression becomes that. So they're identical at R equals B. Both this equation and this equation give you the same result. The question is, what happens when you get down to the other part here? What happens when you get close to A? Well, it turns out if you plug in A here, it actually becomes this. And you might say, whoa, wait a second. Yeah, if you think about it real quick, you'll actually end up with a where this is A down here as well, you actually end up with an expression that is equal to 0. And so it turns out this equation is also equivalent down here. And yeah, also equal to A. If I put it down there, it's valid all the way here. So all of these equations are contiguous or continuous. Finally, I didn't actually draw this one. I'm just going to manually do it. If you created a graph of magnetic field versus distance, um, you would end up with an expression that would look something like this. So A is at 2 centimeters, B is at 1.8, and the other one's at 0.4. What's this going to look like? Well, it's going to increase linearly out to here, and you can actually figure out exactly what that value is. Now you have numbers on it. I'm just going to do it qualitatively. After that, it decreases as a 1 over r squared, or 1 over r term. That's the second one here. And then when it gets to here, it's going to decrease again until it actually reaches 0 when you get to 2 centimeters. And the expression here is actually not very pretty, but it decreases like something. It's got a curvature to it, which I'm not showing. And you could actually find the values at this point and this point and actually indicate these on the values here. I'm not going to plug those in. I'll let you do this one on your own. Good luck. Have fun with this one, and we'll talk to you soon.